Multivariable Calculus, Section 13.9, an extension. Parameterization of a surface. The following little cartoon is how I sometimes feel at the end of a lecture on calculus. How was the lecture? Brilliant, Professor. Thank you. What impressed you? Your total integration with the subject and your disintegration of the audience. Out. Hello. Well, as I was preparing this lesson for the section on change of variables, I kept thinking in my head, this must be like use substitution in single variable calculus. So evidently I didn't quite wrap my head around it, because at the end of the section I'm thinking, that's nice, but now what? It's the end of the chapter. Is that it? Well, in the next chapter on vector fields, this whole concept came back to bite me. And so I started thinking, I need to think of this a different way, because this use substitution idea just isn't working. So I did something, I have to confess, I did something terrible. I went to Khan Academy and watched their introduction to surface integrals. Well, they attacked surface integrals completely differently than our text or MIT video lessons. And it was at first kind of annoying because they used different letters and different notations. But then a light bulb went on and I said, OMG, this isn't about use substitution. It's about parameterization. So I'm giving you a little heads up. This is more than you need for this section, but it's going to come in handy for the concept when we use it in the next chapter on vector fields. Okay, so here we go. Recall the parameterization of a curve. A lot of times we think of t as time and then the points on the curve as the location of some object at time t. Now that real-life concrete example doesn't quite translate into the higher levels of surfaces and so on, but it's a nice concept for when we're learning parameterization. But in general, a more general idea of what this is that we are mapping a number line onto a space curve using three single variable functions: x equals one function of t, y equals a second function of t, and z equals a third function of t. So we're doing a transformation from a straight line onto a curve. And usually we don't think about going backwards from the curve onto a straight line, but in some applications that's exactly what we do. We go from a complicated situation back into a simpler situation in order to do our calculations. Now t is called the parameter in this case, and the domain is a set of points on the t number line, or the set of real numbers t, and then the range is a set of points on the curve, or the set of ordered triples, x, y, and z. Now notice that for a curve we only need this one parameter t, but to parameterize a surface we will need two parameters. Khan Academy names these parameters s and t. Our text uses u and v, and in two-space this concept is quite limited. In two-space we only go back and forth from a flat rectangular area and a flat curvy area. So we have transformations that will take us from a simple rectangular area, for example in the UV plane, to a complicated curvy area in the XY plane. And the main use is transforming a complicated integral in x and y into an easier one in u and v when the region in question is neither vertically or horizontally simple. So what we actually do is take the region in the xy plane on the right and change it into a nice rectangular region in the UV plane on the left. So we actually do a t inverse, a transformation in reverse. Parameterization of a surface. So this time what we're doing is we're not mapping a number line onto a curve, we're mapping a flat area onto a curved surface in three-space. We are mapping a nice flat portion of the UV plane onto a curved surface in three-space using a transformation consisting of three functions again. X is the first function of UV, y is the second function of uv, and z is the third function of uv. Notice that this time they're multivariable functions, functions of two variables, because we're taking a point with coordinates uv and mapping it onto a point with coordinates x, y, and z using three functions. U and v are the parameters. The domain is a set of points on the UV plane that we're using, or ordered pairs, and the range is a set of points, or ordered triples, on the curved surface in 3-space. So it's the same idea, only with two variables as parameters instead of one variable as parameter. Now there's a relationship here between parameterization and vectors that you've seen before, but we're going to reiterate it in this framework. So again, here's our picture. We have our three multivariable functions that map the point uv onto a point x, y, z. And that parameterization can also be expressed as a vector, where r of uv is the vector x, y, z, where x is the first function of uv and y is the second function of uv and z is the third function of uv. And of course we can write that with the chevrons notation or with the ijk notation that's popular in physics. And so now we've seen that change of variables can be viewed as a parameterization. Why is this important? Immediate usage will be, this concept will give us a mechanism for rewriting difficult or impossible integrals in terms of easier integrals, usually with fewer variables. Additional usage. This concept gives us a mechanism for utilizing vectors and then working with vector fields in 3-space. Other usage. The concept of mapping is important in higher mathematics. For example, Andrew Wiles proved Fermat's last theorem in 1995 in part by mapping Fermat's number theory problem onto an elliptical curve problem. So the concept behind all this is very important. And that's why I felt I should spend a little extra time now rather than later in the next chapter. So now I leave you with an elliptical curve. I have no idea what's going on here, but it looks interesting. So you can look forward to this maybe in your studies as you pursue higher level mathematics courses. Do 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 do.